There's only one thing that will defeat my plan to conquer the world. Superior enemy forces? No, rust. We are continuing our discussion on electrochemistry, and here's an application of electrochemistry. Here's a boat that's simply rusted out. How do you stop it from happening? You put a metal on there, or a compound, that will react before iron will. And that's the whole idea of what we're talking about today, that different materials have a different susceptibility. They react, they want to react more energetically than other compounds. So we're going to have a table of all these compounds, and there's going to be a lot of chemistry and insights in there. So we'll talk more about these sacrificial anodes next class period. So we'll just leave it at that for now, but you can do a lot of rust protection, and it's done all the time. We need to get used to some conventional terminology. For example, when we hear cell potential, cell voltage, electromotive force, EMF, E-cell, they all refer to the same thing. When we were drawing those cell diagrams and making those nice pictures, we drew a voltmeter, and we drew a V with a circle, right, to measure our volts, and that were being produced in our galvanic cells. This is an example of a voltmeter. If I turn it on, I should be able to read the volts on this battery. If you recognize the battery is a 9-volt battery, so if I hook up the black or the ground to negative, the red to positive, I should read 9 volts. I read a little over 9 volts. The reason why is they always do that so they can bump up their expiration dates by a few years, but that's the idea. What would happen if I switch these two around? I didn't follow convention. If I didn't follow convention, what changes? Let's switch them around. Same number, just a negative sign. So that's why there's a convention of always having anodes on the left in our electrochemical cells and cathodes on the right. So we're measuring things correctly. Right? So anode, cathode. Maximum electrical work, symbol Wmax. By knowing Wmax, we can answer questions like, just how much work, how much energy can I get out of this battery? Because energy is work, work is energy. How much energy can I get out of this battery? So homework questions are going to look like this. Find the maximum electrical work when 45 grams of silver solid is produced in a voltaic cell with EMF of 1.15 volts, and they give us a reaction. So what we're going to do is we're going to find this Wmax using this equation. And what are all these numbers? F is the Faraday's constant. And what it is, it's the charge on 1 mole of electrons. So there's 96,485 coulombs per mole of electrons. That is F, 96,485 coulombs per mole of electrons. E cell, what's that? That's what the voltmeter reads. So its units better be volts. Okay, one left. How do you get little n? Hint, n is the number of moles of electrons involved during the reaction. So in this case, what we're going to need to do to get Wmax, right, if we're going to solve this problem, we need to get little n. And what we're going to do is we're going to convert that to moles of electrons. We're going to convert 45 grams of silver solid to moles of electrons. Now, to convert from one compound or one species to another, we need a mole bridge. We need a reaction. So let's see if we can work this out. Wmax equals minus N F E cell. Well, that equals minus N. F is 96,485 coulombs per mole of electrons. And E cell, they said, was 1.15 volts. So the only thing we need to do is we have to find N. We find N, plug it in, and we get our W max. To find N, we are going to convert those 45 grams of silver all the way to moles of electrons. That's what we need to do. So let's start with the 45 grams of silver. What mole bridge are we going to use? Well, here's a mole bridge. We have 2 moles of silver solid for 2 moles of silver ions, but electrons aren't in there. We need to use the half reaction. So let's write the half reaction that involves silver ion and silver solid. Our half reaction is silver ion goes to silver solid. That's the half reaction that's involved with silver, so I'm writing the half reaction for silver. To balance it, I need to add 1 electron on that reactant side. Okay, now I'm ready. You see the mole bridge? I have 1 mole of electron for every 1 mole of silver. That's all I needed. So let's convert this into moles. Silver. So silver's molar mass is about 107.9. My mole bridge, 1 mole of silver for every 1 mole of electrons. Now it should work. Grams of silver cancel, moles of silver cancel. I'm in moles of electrons. 45 divided by 107.9, I get about 0.417 moles of electrons. So now I can find W max. So my W max is going to be minus 0.417 moles of electrons times 96,485 coulombs per mole of electrons times 1.15 volts. My W max is going to be about 4.6 times 10 to the 4th. Negative 4.6 times 10 to the 4th. Now, units are joules. Remember, work is energy. Energy is work. And why is it negative? It's negative because we are losing energy, right? It's like a battery. If you calculate W max for a battery, it's going to be negative because that energy is lost from the battery. Standard cell voltages, i.e. E0 cell. So the 0 means standard. So there's some real power here. Let's take a look at something. Look at the one that says 0. They call this the standard hydrogen electrode. Now, why is that a big deal? It's a big deal because if you make a couple cells, let's make one of these be the standard hydrogen electrode, and then the other one, it can be anything. Pick one of these guys and put it there. Right? Measure the volts, and we will always get this E0 number. Okay? That's how they made this table. See all these voltages, all these E0s? See all these E0s? That's how they made this table. Now what's really curious is let's remove the standard hydrogen electrode and put another one of these in here. So now we made electrochemical system, and both are from this table. We can predict what the voltmeter is going to read, okay? And that's the game that we're going to be playing in a little bit here, okay? But let's just play around with this a little bit. Use a table of standard reduction potentials, that's what that table is, to obtain half-cell potentials for each half reaction below. So find this one. Nickel plus 2 electrons goes to nickel solid. Now notice, if we clean this up, electrons are always being added, right? Electrons are always being added on the reactant side. So things are always getting reduced. That's why they call these reduction potentials. So electrons are always on the reactant side. Okay. You're never going to see a table of standard oxidation potentials. You won't see it because it's too redundant. All it is just flipping all these reactants and products, and then they change the sign. So you're not going to see it. You're always going to see just standard reduction potentials. Electrons are always on the reactant side. So for all these. Just wanted to point that out because it's easier to find things. Nickel plus 2 electrons. So you need to find it just like it says right here. Let's see. There it is. Negative 0.25 volts is what it says. Okay. Find the standard cell potential for the reaction flipped. Well, here's the reaction. If we flip it, all we do is we change the sign, flip the sign. So my E0 will be positive 0.25 volts. That's why they don't have a table of standard oxidation potentials. What if we multiplied this top equation through by 3 and we ended up with C? What changes with E0? Nothing. It's an intensive property. It's kind of like density. It doesn't matter how much you have, this property remains the same. It's a potential. Find the overall cell reaction and standard EMF for the voltaic cell. So the overall cell reaction, remember the game plan there is to add up the half reactions, cancel out the electrons, and whatever we get, that's our final answer. Standard EMF, that's the equation where E0 cell equals E0 cathode plus E0 anode. So let's go ahead and see if we can find these. We have nickel solid going to nickel plus 2. And you can just figure it out or just look at the table, but it has to be 2 electrons here, right? And we said nickel solid going to nickel plus 2 was a positive 0.25 volts. The other half reaction is silver ion going to silver solid. So silver ion going to silver solid. We need to balance it. 1 electron, right? Silver ion going to silver solid. Electron is on the reactant side, so we should find it just as it's written. Here it is. Silver ion going to silver solid, positive 0.8 volts. Positive 0.8 volts. They wanted to know the overall cell reaction. Okay, so add them up. You have to add them up so the electrons cancel. Multiply this one through by 2. So then the 2 electrons will cancel. So we would end up with having nickel solid plus 2 moles of silver ion produces nickel 2 and 2 moles of silver solid. And what is my overall voltage? Remember, when you multiply through by 2, you don't do anything to the voltage. Keep that potential the same. 0.25 and 0.8 is about 1.05 volts. So there's my answer. Here's my standard EMF. And here's my overall reaction. What maximum work can be obtained from 28 grams of tin in the below cell if the EMF is 0.55 volts? So you remember, W max is minus NFE cell. Okay, so the only thing we need, we know F, we know E cell, just have to find that N. Do you remember how we did it? Right? Find N. How we did it is we converted 28 grams of tin, convert that to moles of electrons. And how do you do that? You need a half reaction, right? So according to this, we have tin going to tin plus 2. But how do you finish that half reaction? Electrons added to the most positive side. Need 2 of them. So there's our mole bridge, 1 to 2. Start with the 28 grams of tin. What's my molar mass? Tin is about 118.71. According to my mole bridge, I've got 1 mole of tin for every 2 moles of electrons. So 28 divided by 118.71 times 2, about 0.472 moles of electrons. So now I'm ready to find my W max. Minus N, 0.472 moles of electrons, times F, 96,485 coulombs per mole of electrons, times my E cell, 0.55 volts. All right, that's my E cell. So W max should be 0.472 times 96,485 times 0.55, about a negative 2.5 times 10 to the 24 joules. Find the overall cell reaction and standard EMF for each cell. Okay, so let's see if we can break it up into its half reactions. Look up the standard E cell for each half reaction and add them up to get the overall standard EMF for the cell. So you have chromium going to chromium 3, add electrons on the most positive side. You have iron plus 2 going to iron solid, add 2 electrons over here. So let's see if we can get our E zeros. Chromium going to chromium plus 3 electrons. Here it is, but it's reversed, right? So that has to be a positive 0.74. 2 electrons plus iron 2 forms iron solid. Here it is. Iron 2 and 2 electrons forms iron solid. It's written as it is, so just copy it from the table, negative 0.44 volts. Okay, to get the overall cell reaction, I'm going to have to do some multiplying here because you have to get those electrons to cancel. Let's take this one times 2, the bottom one times 3, because then I'll have 6 electrons that'll cancel. So the overall cell reaction, 2 chromiums and 3 iron 2s forms 2 chromium 3s and 3 moles of iron solid. So there's my overall cell reaction. But what's my overall standard EMF? Positive 0.74 and a negative 0.44. It's a positive 0.3 volts. One more. Do the same thing for this one now. Break it into its half reactions. Add up the half reactions so the electrons cancel. Look up their standard cell potentials. Add those up, and you get the overall E cell. Tin goes to tin plus 2 electrons. The electrons are on the product side, so I have to look for this reaction reversed. Tin plus 2 electrons forms tin solid. Flip the sign, positive 0.14 volts. The lead half reaction. Lead 2 plus 2 electrons, lead solid, negative 0.13 volts. It looks like the electrons are going to cancel just as written, so just add things up then. I'll have tin and lead 2 forms tin 2 and lead solid. And I'm left with a positive 0.01 volts. Okay, so what we kind of worked on today was all centered on this, in my view, was centered on this table of standard reduction potentials. That you can use this table to predict just how energetic a reaction is going to be.